So we will continue examples of distributions. So let us briefly recall what we have been doing up to now. So omega contained in Rn is an open set. D omega is the space of test functions. That means C infinity functions with compact support in omega. The support is contained in omega, and the topology on this is dictated by the sequences. So phi n goes to 0 in d omega, so that means support of phi n is contained in a fixed compact set for all k, and phi n and all derived sequences converge to 0 uniformly on k. So this is this thing, and the dual space, so this is the dual space equals so dual space, which is a space of distributions. So t in d prime omega and phi n goes to 0 in d omega implies t of phi n goes to 0. So this is what we have to check when something is to be called a distribution. So the first example which we saw was if f is locally integrable on omega, that means mod f is integrable on every compact subset of omega, then you have that f defines a distribution, namely Tf of phi equals integral on omega f phi dx. Okay, so this defined distribution, and we also saw that if you have two locally integrable functions giving the same distribution, then the two functions have to be equal almost everywhere. So between f and Tf you have a one-to-one correspondence, and therefore very often we will just say a function is a distribution. By that we mean that the function generates this distribution which is defined in this fashion. Okay, so now the next example. So this is called the Dirac distribution. This is almost the starting point for the search for a proper theory. People like Dirac and Heaviside, they used some kind of symbolic calculus which made no sense to the mathematicians, and it was an attempt to clarify what is going on, but yet they were getting reasonable results out of these. And so an effort to clarify these things led to the discovery of the theory of distributions by Laurent Schwartz, for which he got the Fields medal. And therefore, so let us say what is so x is in Rn, and you define delta x of phi equals phi of x. Okay, so this is called the Dirac distribution concentrated at x. So Dirac distribution concentrated at x. Okay, so that this is a linear functional on phi is clear, and also the if phi n goes to 0, then automatically phi n x goes to 0, and therefore we have that this is a distribution in a very trivial way. Okay, so there is now let us this distribution. So if x equal to 0, the origin, then we denote delta 0 by just a symbol delta. So delta, this is usually the famous Dirac delta function which you might have come across when studying differential equations, for instance. Okay, so now this distribution is not included in the previous example, namely the Dirac distribution does not arise from a locally integrable function. So assume the contrary. So there exists f in L1 log of Rn such that integral f phi dx on R, let us say we will just take R for the purposes of this argument, f R equals phi of 0. So assume there exists a phi, so we take n equals 1 now. Okay. So suppose this is true. So now you consider for every epsilon positive arbitrarily small. So you take phi epsilon in d of R. Okay, let us do it in Rn itself. Okay, Rn. Okay, phi in d of Rn such that 0 less than equal to phi epsilon less than equal to 1, phi epsilon support of phi epsilon is contained in the ball center origin radius epsilon, and phi epsilon is identically 1 on the closed ball with center 0 and radius epsilon by 2. So we have seen that we can construct such functions. So origin value phi epsilon of 0, so delta of phi epsilon is phi epsilon 0, which is equal to 1 all the time because of this particular construction. On the other hand, this is given to be equal to integral over Rn of f phi epsilon dx, and that because phi epsilon has support in the ball of radius epsilon, this is just the integral of b0 epsilon of f phi epsilon dx, and that is less than or equal to, because phi epsilon lies between 0 and 1, this is b0 epsilon mod f dx. But f is a locally integrable function, in particular it is integrable on the unit ball for instance, and if epsilon goes to 0, the measure of b0 epsilon, this is the Lebesgue measure, this goes to 0, and this implies by the absolute continuity of the Lebesgue integral that integral b0 epsilon mod f dx goes to 0. So on one hand you have something which goes to 0 and it's also equal to 1 at the same time, and that is not possible, and therefore that gives you a contradiction. So the Dirac distribution is a new object, it does not come from the functions. Okay. So now next example, measures as distributions. Okay, so we will take mu either to be a positive measure, measured in the usual sense, or a signed measure such that mod mu of k is finite for all k contained in omega compact. So again omega contained in Rn open set is a standing hypothesis. So what is mod mu? If mu is a positive measure, then mod mu is the same as mu. If mu is a signed measure, then you can write mu as mu plus minus mu minus, where mu plus mu minus are positive measures, and you have mod mu is nothing but mu plus mu minus. So this comes from when you have studied the sign measures, you would have come across this Jordan decomposition, Hahn decomposition, etc., which tells you that every sign measure can be broken up as a difference of two positive measures, one of them being finite. Okay, and so this has to be finite on every compact set. So then if you for instance, the locally integrable function gives you a sign measure. So integral of g d mu f, if f is a locally integrable function, this is nothing but integral f g dx. Okay, so this gives you how a locally integrable function can give you a sign measure, and because of local integrability, this means that this is finite on every compact sets, because mod f is integrable on any compact set. Dirac measure is also a finite measure and therefore automatically comes in this. So both previous examples are covered by this particular example. So we now define T mu of phi as integral over omega phi d mu. Okay, so this is well defined because mod T mu of phi is in fact just integral over the support of phi d mu, which is less than or equal to norm phi infinity integral mod mu of support of phi, and this being a compact set, this is finite and therefore this is well defined. So again, if phi n goes to 0 on d omega, in d omega, you have mod T mu of phi n is less than or equal to norm phi n infinity into mod mu of k, where the support of phi n are all contained in a fixed compact set K. Again, this is finite and this goes to 0 because of the uniform convergence of phi n, and therefore T mu of phi n goes to 0, and therefore T mu defines a distribution. So this way we define a new distribution. All the measures, sign measures which are finite on compact sets will define another distribution, and this covers both the case of locally integrable functions and the Dirac distribution. The Dirac distribution comes from the Dirac measure. Okay, so this way we have this. Now we will define another distribution example. So this is called the doublet distribution. Okay, so what is this? So this is, you define for phi in d of r, for instance, you define the following. So I will call it delta 1 of phi is equal to phi dash 0. Again, this is linear and it is continuous, because if phi n goes to 0, then phi n and all its derivatives go to 0 uniformly on the supports, and therefore phi n dashed of 0 will also go to 0. So clearly this defines a distribution. So delta 1 belongs to d prime of r. That is obvious. Okay, so this is called the doublet or dipole. So doublet is also called the dipole distribution. Okay, so now and this is familiar to people who have done some mathematical physics. Okay, so now this the doublet distribution does not arise from a measure. Okay, so this is a totally new object. So up to now we have been gradually using familiar objects to define a distribution. We use locally integrable functions, we use measures, and we saw that the sign measure covered everything up to then. And now we are having a new object called the dipole distribution, and I claim that this does not come from any other any measure or anything. So assume the contrary. So there exists a measure mu which is finite on compact sets, as in the previous example. So either mu or mod mu if it is a signed measure, and so we have that phi dashed of 0 is equal to integral over r phi d mu for every phi in d of r. Okay, so we are assuming this, and we should get a contradiction. So we now take a function phi in d of r such that 0 less than or equal to phi less than or equal to 1, support of phi is contained in minus 1 1, and phi is identically 1 on minus half half. Okay, and we are going to define psi k of x is equal to sine of kx times phi of x. So, you are multiplying a C infinity function and a C infinity function with compact support, and therefore, this belongs to D of R. And what is psi k dashed at 0? So, we are using the product rule. So, this will be k cos kx for the derivative here, and then phi of 0. So, cos 0 is 0, cos 0 is 1, and phi of 0 is 1 because of this property which we have here, and so that will give you k, plus the next term will be sin kx and phi dash, but phi dash will be 0, sin 0 is also 0, and therefore there is no extra term. So, psi dash k of 0 is there. So, now if you apply it to the definition, so you will get k equals integral over r of psi k d mu, and this is less than or equal to mod integral, because the support is in minus 1 1, phi is supported in minus 1 1. So, you have minus 1 to plus 1 of phi x sin kx dx, and then if you d mu, sorry. Okay. So, now sin is mod sin is less than or equal to 1, phi is between 0 and 1. So, this is less than or equal to mod mu of minus 1 1. Now, this is a bounded finite fixed quantity, and it is bigger than or equal to k for every k positive integer. That is not possible. This goes to infinity, this remains fixed, and therefore, you do not have any, so this gives you a contradiction. Okay. So, we have now seen, as I am repeatedly saying, functions have been, locally integrable functions have been regarded as distributions. Measures which are finite on compact sets are also regarded as distributions, and then we have also produced some new objects which are called like the doublet distribution, which does not covered by any of these things, and therefore that gives you a new set of distributions. So, we have plenty of interesting examples of distributions. So, before proceeding further, so I just wish to state a theorem. I will not prove it because I will tell you why. Okay, so let omega contained in Rn be an open set, then the following are equivalent. One, T belongs to d prime of omega, that means T is a distribution. Okay. Then 2, for every compact k contained in omega compact, there exists C, which is C of k greater than 0, a constant, and n equals n of k, a non-negative integer, such that mod T is less than or equal to C times norm phi n. Okay, so what is this norm phi n? So, norm phi of any integer m will be equal to the max of mod d alpha x, where x belongs to omega, and okay, oh, I haven't used this notation. You are don't know this notation as yet, so let me not write like this. Maximum of all of phi and all its derivatives up to order m. Okay, so this is the norm of this. So, there exists a constant n which depends on the compact set, a constant c such that mod t phi is set. So, this is an equivalent way of looking at a distribution. Now, this result we will not prove because it involves the nature of the topology of d of omega, which we have deferred for the moment, and therefore we will just accept it. Now here we have, if n equals n of k is independent of the compact set K, that is the same integer works for all compact sets, then we say that T is of finite order. This n is not to be confused with the dimension. Okay, maybe I should change the notation. So let me say m equals m of k, and then I change it to here. So namely m. Okay, so this is called the order of the distribution. If not, we say, that is, if this m depends on the compact set and it changes for everything, we say that T is of infinite order. Okay. So if you look at f in L1 loc, or mu is a measure finite on compact sets, then Tf, T mu, so these are of order 0. This thing is, so this should be for every phi in d omega, support of phi contained in K. Okay, so that is necessary. So this constant will depend on only for these things. Okay, so that is to be it. So here we saw, because we saw that mod T of phi in all these cases was nothing but norm phi infinity times some constant, which was the measure of the compact set or something like that. Okay, so this is nothing but when m equals 0. So you are only taking no derivatives and therefore the same. So doublet distribution is of order 1, because mod T phi is less than or equal to norm phi 1, because it is phi dash 0, and therefore this is true for every thing. So doublet distribution is of order 1. Okay, so now we will continue and define a calculus of distributions. We will define differentiation, multiplication by C infinity functions, etc., which we will look at later.